Hello again, it's Phil Story from Sydney, Australia. Today we're having a deeper look into the NetData flowchart and what Kerry Rogers of Packet Bomb fame calls wizard mode. We're using NetData, so we'll be visualizing IT performance. Visual aspects really do play a part. Of the various charts, we're going to be focusing on the flowchart. That's slaved to the packet timing chart, so we'll have a bit of a look at that too. We'll be doing all of our usual things. The packet capture that we're going to look at comes from an Ask Wireshark question, 5043 TCP slow start, and this is from 2018, so it's a couple of years old, but still it's a good example. This Dropbox doesn't have the PCAP file in it anymore. I'll make the PCAP file available from my own website, and the link will be in the description below. I came a little bit late to this one. Packet Vlad did a great job of answering the question, so I just added some comment into his answer, and it wasn't until December. So here's a slow start PCAP. As usual, we'll drop it onto NetData. Fast forward to the dialog chart, the first place we start, and we can see the color coding here. There's 6% packet retransmission rate. So we get a clue that we're going to be looking for a lot of packet loss. Let's just verify. The Ask Wireshark questioner says he was uploading a file to Dropbox from his home PC. Here we can confirm it's a client-side capture. The server, presumably Dropbox, is about 55 milliseconds round trip away. To save time, I've jumped straight to the flowchart. First of all, we can see the server's receive window. Early on ramps up to about a meg and stays there for the rest of the period. See that even in the very first big burst, it's up to about 180k. We'll zoom into that area later. This part of the chart is very similar to the Wireshark TCP Trace. It's byte on the left-hand scale over time. We can see we get a pretty consistent flow, but there are these little bumps along the way. We'll find out that they're all packet losses and selective acts. The area down here, this beige area, is bytes in flight. Believe it or not, we can essentially tell what the problem is or what's happening right from here, because bytes in flight ramps up until we get these red packets indicating that that's where we had packet loss, and what it's telling us is that, I'll lock that on, Alt-Z. If I do a couple of these Alt-Z around under those red packets, and what we can see is that there's always packet loss when we get to roughly 100k, and it's pretty consistent. Alt-R. So we have a ramp up of bytes in flight, and as soon as we get to 100k we have packet losses, and we back off and we ramp up to 100k again and we have packet loss. 100k packet, ramp up to 100k, packet loss, and there's the corresponding packet loss areas up there. We can also tell that this must be a relatively modern TCP stack, because it's not the traditional sawtooth, it's more of a cubic pattern. We can see it's a curved ramp up, a horizontal part, and then a curve up again. Same here, horizontal part, curve up, relatively horizontal, curve up. And we can also tell from here it doesn't seem to affect our throughput much, so we can verify that. Format, data throughput, replot, and here's a throughput line. Seems to be a little bit over 1 meg. As the congestion avoidance algorithm lets us ramp up, then we get a ramp up in the speed, and then we get a packet loss and we back off, and then we go through the whole ramping up process again. We have a fast ramp up, we hit 100k bytes in flight, and we have some packet loss. But what kills us is when it ramps up to faster than that. So as soon as it ramps up faster, we hit this zone, packet loss. Ramps up, packet loss. Ramps up, packet loss. So we've got an idea of what's going on now. There's a downstream 100k buffer somewhere. So what can we do to validate our hypothesis or seek further confirmation? Well, one thing we can do is format. We've got the throughput line on, but I'll change it to be the ACK throughput. And what this will plot is now the throughput that the receiver saw. And we calculate that based on the ACKs that come back. And you see it's pretty much smoother, essentially right at the 950 mark, which, given that the throughput line here is measuring TCP payload bytes and it's not the headers, we're pretty much getting the 1 gig that was stated in the Ask Wireshark question. I'll turn off throughput, and what I will turn on now is trip time. And what we get now is per packet trip time. It looks a bit scary, but it's really quite simple. So for these data packets that we see here, there's a little black square indicating the trip time of that particular packet. So the very first one down here, Alt-Z, had a 57.8 millisecond round trip time, which is pretty much the normal round trip time that we measured. But as the subsequent data packets flow out, the round trip time of each of them ramps up. As we send them faster, the round trip time increases faster, and we get to a top here of 843 milliseconds. So there's a downstream queue. The first packet gets through straight away, but the last packet is in that queue for close to 800 milliseconds. So that's confirming what we suspected, that downstream from us, our local home router presumably, there's a queue. It's sending data out to the internet at 1 meg, and we're sending data to it at something a little bit faster. So it has to queue the packet. So let's zoom into the beginning and get a closer up view. It was called no slow start. The trip times are still turned on. And as we can see, even at this scale, as we send more packets into the queue time takes longer and longer. The black round trip times are increasing, corresponding to the right-hand scale here. And there's even a little blue star. This is a trip time for the initial SYN packet, and that can confirm that our connection setup time was 55.7 milliseconds. That's what we would consider the minimum round trip time. And we also see that one of these very early packets, 56.9. I'll turn the trip times off, and then I will zoom right into the beginning, and I'll also reduce that in-flight area down there, the beige area. There was one packet all by itself, and it had a client hello, because this is an SSL connection, and it was only 575 bytes. This little line here is the server's receive window, Alt-Z. In the SYN that we saw right at the beginning, the server advertises a receive window of 28K. So far we've sent 575 bytes into it. There's a round trip time. Here's the ACK for that first data packet, and based on that ACK we now will send more data. Now these are very small packets too, for whatever reason, and so we end up with an 11 on the top, but if we look at this, it's actually 10.3 segments worth, where a segment is the MSS. So my hypothesis here would be that the sender, we've already said it's a fairly modern TCP stack, so it's doing the slow start beginning at 10. It's actually 10.3, and possibly it's making up for the remaining data that it was allowed to send after that first one. What's interesting is that we don't double. So if I right click at the right and we'll double the time scale, we see the server's receive window ramping up over time. We see the ACKs coming back, and when we get an ACK we send more data, and we get some ACKs we send more data. But the count here of the little numbers bytes in flight are both on the bytes in flight area down here, or the congestion window, and we see it ramping up fairly linearly, and the same numbers are on top of this. So 13, 14, 15, 17, 19, 20, 23, 25, and once we get up here we seem to be increasing the packets per round trip by 2, and that continues. Notice that the server's receive window keeps moving up ahead of our congestion window, but we do see something interesting. There's some red attachments to these packets. That means that as we got to this area here we start having packet losses. We can see that that area is around the 100k mark, and we also see that we keep getting packet losses, which gives us about 100k getting through, even though we've actually transmitted more. At this point in time we've transmitted 146, and at the height here we have Alt-X, Alt-Z. We've actually transmitted 183k, but only 100 is made it through, and we have this area here of 80 or 56 segments assumed lost in transit. So a couple of other visual aspects. We've got the little red tick to say these data packets were lost. We've got the rate of those packets being faster than the rate of the ACKs coming back. The server receive window is 184k. At this point in time we have exactly filled it up, 184,320, 184,320, and therefore we have to stop transmitting. Go to the right again, and a very interesting area here now. I'll zoom in a little bit and I'll do this fixed sequence scale. I'll change it to this so that we can do this kind of zooming in. Now, this gets interesting. We've seen selective acts before, and so we know that the cross-hatched area is data we didn't get. The blue area is data we did get. Didn't get that, did get that. That's left edge, right edge, left edge, right edge, left edge, right edge. So at this point in time, there was a selective act that had 4 left and right edges in it. Let's confirm that. We'll go to the packet timing chart. These are the data packets that we're sending. These data packets got lost. The retransmission of these data packets was all the way over here. And another interesting thing is that normally these packets were 1440, but the retransmissions start becoming 864 and 576. And you add those up and we'll get the 1440. Here we see normal blue normal acts, and now we get these purple selective acts. So the first selective act got 1 left and right edge in it, but notice how they get bigger as they get more and more, and when we get to this size, Alt-Y, Alt-Z, then we have the selective act data is left, right, left, right, left, right, left, right. So it's got 4 left, right edges, and that's as many as you can have. Another interesting thing to note while we're here is over on the right, we started off with normal blue diamonds, which are normal act, then we had purple selective act, and then we get some green DSAC. So duplicate acts, again with 4 pairs of left and right edges. So let's go back to the flowchart. Because you can only have 4 left and right edges in a selective ACK, then these later selective ACK have forgotten about the data that was actually ACK earlier on. But NetData will allow us format, accumulate selective ACK information, and NetData is now going to remember the blue zones and the crosshatch zones. The first selective ACK we received said 1 left and right edge. I received the light blue, I didn't receive the crosshatch. So we didn't get 2, we did get 1. And in response to that, the sender sent a retransmission. So this is a retransmission of a data packet to the left, which would have had a red attachment to it. And you can see this step up on the left is as more selective acts come in, and there's more left and right edges. Now over to the right, there's another data packet that's actually, that is a retransmission. It's the same sequence number as this one. So what's going on here? If we do an alt drag, we lock onto that packet and we lock onto the retransmission, and we can see, if you look at the top right, that that's 677.29 milliseconds. Because I've done an alt drag, I now get this green line. I'll do an alt R and I'll get these pop-ups again. And this time, pop-ups have got this little timing information. It's like the relative time is reset to 0. And so if I come over here, Alt Z, we can see that this retransmission of that same data was 677 milliseconds late, but the ACK to that first retransmission came back 790 milliseconds. And that's because this data packet hit that big queue. It was held up 740 milliseconds. So we saw that packet leave here then. It was held up in the queue in our local router, and it got to the other side, and the other side ACKed it, but the ACK didn't come back until 790 milliseconds later. But in the meantime, 677 milliseconds later, we had a retransmission timeout. This is a fast retransmission. This is a retransmission after a timeout. Now you might say, well, this ACK, is this ACK in response to that packet, or is it in response to that packet? Now that we do get a confirmation of which way around that is, and that's because over here at the same level we have the DSAC. So the DSAC is saying, you sent me this data twice. So we know the receiver didn't get this data packet when it was black over to the left first time. It did get the retransmission here. It did get the second retransmission. The DSAC is in response to the second one, and that's all the way over there. So this ACK here is in response to the first. The visual aspects of NetData really come into play, because purple packets are retransmissions, cross-hatched areas are selective acts saying I didn't get it, light blue areas are saying I did receive. And what we can see, so these are all fast retransmissions in response to the selective acts. They fill in the cross-hatched area. There's no retransmission in the light blue area. So all of these retransmissions are fast retransmissions based on the selective act. So I think the way of drawing this and seeing the packets fill in the cross-hatched area is just a great confirmation of what's going on. So all of these will be retransmission timeout. We get up to 54 packets again. So we're pretty much going to fill up that queue with all these retransmissions that we don't really need. And here we can see that these retransmissions actually fill in the light blue areas. So the sender just decided, I'm just going to send everything again, forget what I've learned through the selective acts. Just something else to point out while we're here. These little numbers below the ACK line are the duplicate ACK count, and in this case the duplicate acts are also SAC, but 1 and 2 are green, and then 3 is purple, and that's because the third duplicate ACK is the one that would cause a retransmission. Purple is the color of retransmission. A little subtle visual hint that NetData does for us. I'll right click and go to the right, and we also get to see all of these unnecessary retransmissions have this fast slope, and all of the DSACs coming back have this slower slope. That's confirming that we have queuing and the receiver is receiving the packets at a slower rate than we're sending. Just something else to point out while we're here. Notice here we'd filled the receive window, and notice that the server's receive window actually drops a little bit and then it ramps back up again quite quick. Now something else of interest, so the first retransmission timeout is 500, the second retransmission timeout is 1.5, and all of these, again, we get these DSACs that say, hey, you keep sending me the same data twice. We'll go off to the right, keep clicking to the right. Oh, I'll go back to normal fixed scale. We see down the bottom, we ramp up fairly slowly. The ramp up gets quicker. We hit about the 100k in flight again, and we get packet loss. Even from here, we can tell that this selective ACK area is not as dense as this one, so the losses are not quite so bad the second time around. But there is something interesting here. The sender stopped transmitting at this point, presumably because we've hit the congestion window. When we got some ACKs from the receiver, so the ACK line here jumps up, then we can send more data, and we send a big burst, and we get this sort of repeating pattern of big burst. My hypothesis here is that this is the rate the data packets are coming off the hard drive of the PC. When we had to stop because we filled the congestion window, the application kept reading the data off the disk into memory, and then when we can go again, we can send a really fast blast because we're pulling it out of memory. Then we have to stop again, we wait, get more ACK, more blast. Just something interesting. And then of course here we have these packet losses again, and we're into this whole selective ACK business. So this time it wasn't bad enough to trigger all of those unnecessary retransmission timeouts. So we get through this much more quickly. And then we see that as we start ramping up, the server's receive window starts ramping up pretty quickly. So the server has decided, well, this guy's sending me a lot of data, I'll prepare myself. So again, some rich data there, courtesy of NetData. Here's my details. Next time we'll be looking at the waterfall chart, and we'll be back to looking at transactions.